Good morning. This question is from Resnick and Halliday. And as you can see, there is a square loop of side 2 meters, and there is a magnetic field which is shown to be dots. So, dots are the magnetic field direction, which is all right. So, before I move forward, just one point. A lot of students have confusion in this question, which is very basic in nature but needs a quick look, is on the dot and cross sign convention. So if you see a dot in the question, it is inside the page, okay, or the plane. A cross represents the magnetic field which is coming outside the plane, okay, outside the plane. I have seen many students doing mistake in this question because they forgot the sign convention of magnetic field direction. A dot will represent inside, a cross will represent outside the plane. Please never forget this, because if you do mistake in this, you will get a big zero in the exam. Then there is a EMF source, which is a battery of 20 volts in the circuit, and it is given that the magnetic field is time varying. You have to find the net EMF in the circuit and the direction of the net current around the loop. So as you can see, the question is based on the concept of Lenz's law, right? So Lenz's law. Okay, before I solve this question, the first step is to understand the situation. So we will revise the concept first. Let's use a diagram. So for example, this is your area, okay, and you have a magnetic field which is going like this, okay, and it's a case of uniform magnetic field. So all the lines are equidistant, just like this. So this is time varying, although the distance is same, but it is time varying. If you see, it varies with time. So it is not uniform exactly, it is non-uniform, but not because of spacing, but because of time varying. So this is your magnetic field. If you have to consider the flux which passes through this, draw a area vector like this, and then there is an angle between the two, which is the angle between B, which is the magnetic field, which you can see is this, and then there is a area vector which we have drawn as perpendicular to the area. So this is your area, right? This is your area, and then this is the angle between area vector and magnetic field is theta. So the flux which passes through this area is given by B dot A is equal to BA cos theta. It's a scalar product. Now comes the most important part of this question, which is then what happens to the EMF, which is what Lenz's law is all about, right? EMF is calculated as, and I'm just calculating the magnitude. Okay, we will talk about the negative sign also, which helps you to find the direction of the induced current, is given by d by dt, right? As you can see, the differentiation is with respect to time, b a cos theta. Now, depending on what changes, you can break this down into three parts, right? So if b is changing, you write this as db by dt multiply by a multiply by cos theta. This is normal multiplication. If area is changing, then you write this as b cos theta dA by dt. And if theta is changing, you write this as b a d by dt, and you show area is changing, right? Sorry, theta is changing. The inclination, the angle between the area vector and the magnetic field vector is theta. This can also change, as happens in the case of rotation, for example. Now, if you notice, you can have three situations to create EMF, right? And Normally, when you try to solve the question, you have to identify which one is applicable to you. So if we notice this question, is the area changing with time? The square, half the square, it is not changing with time, right? So area is not changing. So dA by dt is equal to 0. Is angle changing? No. So even this is 0. Is dB by dt okay? Yes, it is, because there is a time varying magnetic field. So, okay, so this is the first step you need to think about. Varying magnetic field with respect to time, area which is changing with respect to time, which could mean you have an area like this, and as the time changes, the area reduces, right? So the num the flux which passes through this was earlier as shown as this, right? Now it is this. So area change results in lesser flux. So yes, this is that example. Third is the angle changes, which means the magnetic field remains same. The magnetic field is same. So I'll just draw an area. Area is not changing. The magnetic field is not changing, or the magnetic field could be at an angle. This is just an example. And this particular area loop is rotating like this. Okay, so it is rotating. So the with the rotation, the area vector will continuously change, and therefore the flux will change. So this is the situation of the angle between B vector and A vector, which is changing, right? So we are referring to the angle here. If you see our question, you can clearly see that this is applicable to us. I have already written these to be 0. So we will use the magnitude of EMF to be dB by dt multiplied by A multiplied by cos theta. And as you can see, the direction of magnetic field and the direction of area vector in our question is parallel. All right, so quick discussion again on a very basic concept of understanding theta. This is again a place where a lot of students do a mistake. So if you're given a area vector like this, okay, so this is your area vector, okay, and I'm drawing a square, and you have a magnetic field which is going upwards, okay, so the magnetic field, and this is a straight line, don't worry about the if you see some curve, okay, so this is a uniform magnetic field maybe, and point I'm trying to say, so the magnetic field is in y axis, okay, for example. Now if you were to draw the area vector is also here, okay, this is the area vector, okay, the area vector is also in plus y axis, right? So what is the angle between these two? The angle between them is 0 degree. But consider a situation where this is your area vector, okay, and I hope the view is better now, but the magnetic field is inside. This is the magnetic field. The magnetic field is in minus y axis. The area vector is still upwards. Okay, this is the area vector. So this is your area vector perpendicular to the area, and this is your magnetic field. As you can see, they're anti-parallel. So in an anti-parallel, the angle between them is 180 degree. If you see the question we are given, and I will draw, the dot represents the magnetic field which is inside the plane. I will draw area vector which is coming out, right? As you can see, we always draw the area vector which is perpendicular to the area. So if I were to give you this area, okay, which is facing you, you don't draw the area vector on this side. You always draw the area vector on the side which you see, right? You don't, so for example, in our question, what we see is the area vector, which is this, right? This is the area vector you're seeing. You will draw an area vector which is perpendicular to this, not on the back side, because you see this as a front face. You draw area vector on the front face and you have to draw it like this, right? So in our question, also be very careful. The magnetic field is inside, but the area vector is in this side, and therefore the angle between them is 180 degrees. this is a very important point. A lot of students have a confusion. They do a lot of big questions, but when it comes to very basics, they forget it. And again, what they get in examination is zero, despite being a very good student. All right, so let's continue to solve this problem. And now we just need to substitute the values. Okay, so let me just substitute the value in the expression d phi by dt to find the magnitude of the EMF, right? So let's do that. So this is equal to d by dt. And as you can see, b is given by 0.0420 minus 0.870 t, right, multiply by the area. So area is half the square. This is the area being referred to. So it will be 2 multiplied by 2 divided by 2, right? So just total area of the square is this, half of this, multiplied by the angle. Now we know the angle is, cos is 180 degrees, because we just understood it, that the area vector is drawn like this and the magnetic field is inside. So the angle between them is, so this will become cos of 180 degrees. So we can always solve this. This will give you minus 0.870. dt by dt will be 1 multiply by 2 multiply by minus 1 is equal to, this will become plus, negative sign and negative sign. So this will be 14.7 and this will become 1.74 volts. So now we know the at least the EMF which is getting induced. Now our confusion is, we also have a battery here. So how do we adjust this EMF, right? So do we put the EMF as an additional EMF, which is the one which adds with the existing EMF, or do we add it in a reverse manner so that these two subtract? So this is the existing EMF of, uh, I think it is given to be 20 volts, right? So 20 volts, and if this is the situation of 20 volts, then the situation I have drawn is subtraction, right? These two cells will subtract the potential difference. So either it can be like addition or it can be subtraction. We have to decide that also. And a lot of this will come from our understanding of Lenz's law again, where specifically we will focus on understanding the direction of the current. Once the direction of the current is established, we will be able to understand the direction in which we have to, EMF which has been calculated, the how we add that EMF. So d phi by dt, the negative sign is the focus now, right? This is one focus we have. And the second focus, of course, is negative sign. How do we adjust it? If you see the, so now what are we studying? We are going to study how to decide the direction of the current, which is the part B of this question, if you notice. If you have a current which is getting induced in some conductor in this direction, you use the right hand rule, a right hand rule to find the direction of the magnetic field, right? So the magnetic field for this particular situation will be like this. Okay, the magnetic field is going to be like this. Okay, and supposingly the so we understand, as seen from the top, it is coming out and here it is going in, right? So you can see the magnetic field is coming out here, right? So it is coming, okay. So I have used the right hand rule where the thumb points to the direction of the current, okay. And I will tell you how to use this, right? You need to understand how to use right hand thumb rule to find out the direction of the induced current. And this is the induced current, and it is, as you can see, the curly fingers of the right hand rule show the direction of the magnetic field. Now, as per the Lenz's law, which is the negative sign, is where I'm focusing on. The current which gets induced should be in a manner that the magnetic field should, the magnetic field, right, should be created in such a way that it tries to restore the situation. in our question, the magnetic field is changing with respect to time, right? It's something is happening to the magnetic field. Now the current should get induced in a way that it restores the magnetic field, right? So if you have, for example, let me take you to the diagram, okay, and let me just rub this off so that we're able to only focus on the diagrams to understand this better. And this is a very important part of the question because it also helps you understand how the EMF direction has to be established in the circuit, right? And this is the very most important part of the discussion, in fact. Now, if you notice, assume that the current got generated like this, okay? So I will hold the wire with my right hand in such a way that my thumb points towards the direction of the current, right? So, and if my curly fingers are there, my curly finger, will show the magnetic field to be circles around it. Like these are the circles, and you can see that the magnetic field is coming out, from this. So it is coming outward when it comes to the area where the magnetic field is existing. So you can see the dots are the magnetic field. And if you use right hand thumb rule, you will realize that the magnetic field is coming outward. Okay, it is coming outward. So this is the magnetic field which is associated with the induced current, right? And it is coming outward, so it will be a cross, right? Which means that if you have a magnetic field which is inward, the existing magnetic field is inward. If you keep the current direction the way I have shown you like this, then and this current direction is because of the induced EMF, by the way, okay, not because of this. So the magnetic field is coming out. What will happen? The magnetic field which is coming out and the magnetic field which is inside, they are against each other, right? They're against each other. And what do you want? You want a magnetic field to be in a manner that it restores the previous situation. What is the previous situation? The previous situation is that the magnetic field is inward, right? And you are changing the magnetic field, inducing a current. And if the current is induced in the direction which I have shown in the diagram, the magnetic field is this. If you, for example, now change this situation, and let's say the magnetic field is in this direction. Let's say the magnetic field is in this direction. Now what happens? The thumb will point towards downward right here, and the magnetic field will come outward. So it will be outward magnetic field here, right? Outward means what? Cross here. But inside, it will be a dot. As you move and roll it, the magnetic field will be inside the plane of the paper when it comes to the uh, area which is being considered. This is not the area we focus on. We are only focusing on the area where the changes are happening, right? In a circuit, which is this. We are not considering this part. We are only focused on this particular part of the situation. So you can see if the current is in downward direction, I'm calling it downward to make it simple for you, and you keep the fingers like this, the magnetic field is inside. So the magnetic field in this situation, right, it adds, or so to say, is in the same direction as the existing magnetic field. So this is your existing magnetic field, and this is the magnetic field which is induced by the current, right? What does the negative sign tell you? The negative sign tells you that the current will get induced in a direction in such a way that it opposes the change. It opposes the change. So it will try to restore the original situation. Original situation was what? The original situation is that the magnetic field is inside. If you keep the direction of the current, what is shown to you now, that is in the downward direction, the induced magnetic field is also in the same direction as the existing magnetic field. So it helps restore the same situation, right? It keeps you as is. You're inside, existing magnetic field, what is induced is also inside. So nothing changes. But if you reverse it, the magnetic field will come outside in the area which is the focus, which will mean a change in the situation. So, which is a correct choice? The correct choice is that the magnetic field should be downward so that it restores the original condition of magnetic field being inside the plane of the paper in the area, not outside the area, right? So, if the direction of the current is this, then what is the direction of the induced magnetic field? Obviously, the induced magnetic field, if I were to show it as a direction, I will draw it outside the chosen area, right? If this is the correct direction, then the positive terminal is like this, right? This is the positive terminal. And as you can see, these are now connected like this. So positive, this is the induced, and this is the existing. So you can see these are against each other, right? So they are negative terminal. So it will get subtracted. Whatever we calculated as a small value of minus 1.74 volts or plus 1.74 volt, the net EMF in the direction, right? The net EMF will be 20 minus 1.74. That is the exact answer you will get. So roughly around 18.26 volt is what will be left if you subtract the induced EMF from the existing battery EMF. This is the way you need to solve these problems. These problems require you to think through a lot of things. I have given very basic mistakes you do, and also given you how to apply the Lenz's law and what is the significance of negative. You want to restore your original condition. That is the only way you will be successful. If you can restore your original condition, that is that is the direction of the current you need to choose. So if the answer to B will be what, that the current should be in a clockwise direction, because it helps you restore the original condition back. I hope this helps you understand Lenz's law in greater detail and also helps you analyze this whole question. I could have done this in two minutes directly by just writing some equation and assuming you know a lot of things. But I think the devil is in the detail, and unless you get good explanation, it is pretty futile to watch any video. Let it be my video also. If there is no explanation, it carries no value for you. So don't waste your time watching videos where you have no explanation, because you're purely watching it, you're not learning anything. This is the only channel in the country or perhaps world which aims at giving you explanation. You're not paying anything, you are just watching the video and learning questions from Resnick and Halliday. So thank you very much for your time, and please do spread this channel in your community, in your family, in your friend circle, and let's educate more and more people, in our journey towards 1 million subscribers or 1 million students, which I want to impact. Thank you very much, and see you soon.